Hi everybody and welcome back. Today we're going to be looking at the geometrical proof of Pythagoras' theorem and just kind of revise a little bit about Pythagoras' theorem. So this is Plane Geometry Lesson 6, so thanks for tuning in. Okay, so the goal for today's lesson is to apply the meaning of Pythagoras' theorem and its converse, and you're looking at exercise 4.6. So first up, you need to remember what Pythagoras' theorem actually means, not just the rule. So everybody knows the rule and that's cool, but it's really important that you understand that Pythagoras' theorem only works in right-angled triangles. And it's basically saying the square on the hypotenuse is equal to the sum of the squares on the other two sides. Okay, so basically when you either find the area of this square or you take the square of it, so pretend this is a square, it is equal to the squares on the other two sides. Okay, so that's kind of really important that you know what it means. Obviously this would be a square, but I just ran out of room. So in other words, these two squares in here, the a squared and the b squared, they fit inside this space. Cool. So with regards to the geometrical proof, it is important that you know this one and that you have a read of it and understand it. So I'll quickly go through some of it now. First up, you've got a picture here of a right triangle ABC, but we have drawn this perpendicular CD. Okay, and we're going to let the line AD be X. So I'm going to let this be X here. And I'm going to let DB be Y. Okay, then what I can say is that X plus Y equals C, because that's the small side C here. And then basically we prove that triangle ADC and ABC, so ADC is this triangle here, and ABC is the other one, not shaded. We prove they're similar, and we do that by using similar triangle proof, and that's here. So we've got angle A is common, angle ADC equals angle ABC, which is 90, and therefore it's basically three pairs of matching equal angles. And then basically we use the ratio of sides. So I'm going to go, well, they're going to go really, AC over AB. So AC so this line here, over AB equals to AD over AC. So big sides over the small sides, and that actually equals to B over C equals to X over B. Okay, and then we've got cross multiplying here, the B squareds. So doing that times that and that times that, B squared is XC. Do the same for the other pair of similar triangles as well, and you actually end up getting A squared equals a YC, and you end up with this statement here. So it's a bit of algebra. A squared plus B squared is YC plus XC, factorizing that out, because if you remember in your picture, we've actually got C as being X plus Y. So that's how you actually end up with the C squared term here. And that's a geometric proof of Pythagoras' theorem. So have a read, and if you want to ask me any questions, write them down. Cool. Okay, a couple of problems to quickly look at. Just two. And then you guys can have a go at your exercise. So the first one is saying, in this diagram, angle BAC is equal to angle ACD equals 90. So that's these two here. They're telling me that AB equals 6 centimeters, BC equals 10 centimeters, and CD equals 15. They want me to find lengths AC and AD. So using Pythagoras' theorem and just skipping a line, it's going to be, AC is going to be the square root of 10 squared minus 6 squared, because they've already found the hypotenuse for me. Type that in your calculator and you end up with 8 centimeters. So that's for AC. And then for AD, that's going to be the square root of 15 squared plus 8 squared. And that's equal to 17 centimeters. So that's a nice, easy kind of, extension year 8 problem there for you. Okay, the next question is looking at the converse of Pythagoras' theorem. So in our goal for the lesson, we talked about apply the meaning of Pythagoras' theorem and its converse. Converse of Pythagoras' theorem states that if you have 3 sides that satisfy Pythagoras' theorem, then it's a right-angled triangle. So this question is saying, is this picture here on the right, is that right-angled? Well, how you need to prove this is using the left-hand side, right-hand side proof. Okay, so the left-hand side, and when we say that, we're talking about Pythagoras' theorem. So if we've got c squared equals a squared plus b squared as a rule, then the left-hand side of the equation is on the left of the equal sign, and the right-hand side of the equation is on the right-hand side of the equal sign. So we're going to take the left-hand side. Now we know that c stands for the longest side, and in this that's 61. So 61 squared we're putting in there, and we can work out what that is, 3721. We're then going to take the right-hand side of the equation, which is a squared plus b squared, and we're going to substitute in those sides, which is 60 squared plus 11 squared. And when you work that out in your calculator, you actually surprisingly get the same result. So basically you can say, since the left-hand side equals to the right-hand side, and those side lengths, 11, 60, and 61, satisfies Pythagoras' theorem, triangle ABC is right-angled. Fantabulous. Okay, so what we've actually done is kind of work backwards to prove that the triangle is in fact right-angled because those 3 numbers work inside Pythagoras' theorem. Awesome, so you guys need to write down 3 summary points that you revised or learned, write down any questions you have about this section of work, and then you're trying the exercises again, showing working as I have, and marking it as well. Make sure you're not choosing the same level of homework as well each time. Thanks everybody.